kids. Do you hear the Doppler effect there? Okay, anyway. But this is a little instructional video telling you about torque and equilibrium. So let's actually talk a little bit about what the heck each of those words are. Again, I'm not going to solve problems. If you want that, look at a different video. But this is going to be an instructional video so you understand the basics of it. So let's talk about what they are. So let's talk about torque first. What is torque? Well, a torque, okay, is equal to, okay, force times lever arm, or sometimes you'll see it written like this. Okay, the perpendicular part of the force times the lever arm. I think on your formula sheet, I think it's written like this. But this is telling you the perpendicular force times the lever arm. So let's talk about what the heck that means. Well, first of all, torques are something that causes something to change its state of rotation. First semester we talked about forces, and forces causes things to change their state of motion. If there's a net force, it will accelerate. Well, guess what? A torque is kind of the rotational equivalent of a force, where a torque causes things to change their state of rotation. Or if you like, a torque causes things to experience angular acceleration. Okay? But it's perpendicular force times the lever arm. So let's talk a little bit about what the heck that is talking, or what that means. So let's pretend I have a door, and I got some hinges here. So like right here, that would be my axis of rotation. Okay? And let's say for some bizarro reason, you are going to go and push on the door like that. Well, if you push on a door like that, guess what? It ain't gonna open. It ain't gonna change, because you know what? That's not a perpendicular part of the force. Okay. So like, the other thing we can talk about, like doors have doorknobs over here. Why do they have doorknobs over here? Why not like right next to the hinge? Well, they have doorknobs over here because it makes it easier to open the door. Why does it make it easier to open the door? Because it has a bigger, that would be your lever arm. It has a bigger lever arm. Okay, and of course to open it, you'd want to push this way, or do you want to pull that way, so that it would be perpendicular to this. Okay, but that's really important, guys. You understand torque is force times lever arm. Okay, so anyway, so that's what torque is, at least the basics of torque. And then if we talk about, well, what the heck is equilibrium? So let's talk about that. So equilibrium actually has two pieces. Okay. First semester we did some stuff with equilibrium. Well, what are you talking about? Well, if an object was at rest, it stayed at rest. It was in equilibrium. If an object was moving, it stayed moving at a constant speed in the same direction. It was in equilibrium. So what does that mean? Well, equilibrium means that your acceleration is going to be zero. Well, how do we get zero acceleration? Well, you have to add all your forces up and get zero, which is really Newton's first law, right? It was. If the net force is zero, an object's going to experience zero acceleration, i.e., if it's at rest, it'll stay at rest. If it's moving, it's going to stay moving in a straight line. Okay? So one piece of equilibrium means, hey, you know what? You add all the forces up, you get nothing. Okay? The other piece of equilibrium means this. Okay? That if you add all the torques up, you get nothing. Well, what does that mean? That means if an object is not rotating, it's going to stay not rotating. If an object is rotating, it's going to stay rotating at the same rotational speed in the same rotational direction. So, well, what does that actually mean? That means that the angular acceleration, or the rotational acceleration, is zero. The symbol for rotational acceleration is that symbol for alpha. So like, if it's not rotating, it's going to stay not rotating. Well, how does that happen? That means the sum of the torques equals zero. Okay? So when you're doing problems like this, and I'm not going to work through a whole problem, but in general, what you guys need to understand is when you're doing a problem, you got to draw a free body diagram, which I'll show you an example in a minute. And then after you draw your free body diagram, you're going to write your equations. One equation is going to be, hey, all of my forces have to add up to zero. Maybe you have horizontal and vertical, parallel, perpendicular, whatever. And then the other equation, if it's in equilibrium, all my torques have to add up to 0. Okay? So we'll just let me just do an example for you. Sometimes we have, a problem like this, where you say, hey, I got this dude, he's a window washer or whatever, and hopefully it's in equilibrium, because otherwise our window washer is kind of in trouble, but anyway, so it's going to be in equilibrium. So then what would you do? Well, you would draw your FBD. The only difference is you have to draw an extended FBD. First semester, we drew everything through the center of gravity. You could make like, hey, draw the forces on this dot. Well, you can't do that. Okay, why? Because torque involves lever arm. Okay, so if I was to draw my FBD for this one, it would look something like this. So you'd have, hey, I have one force of tension. Hey, I have another force of tension. Hey, I have the force of gravity from the dude. Force of gravity from the dude. I'm going to call that a dude, sorry. And then I would have the force of gravity, okay, from the board or whatever they're standing on. Where would that be? That would act on the center of gravity of the thing. So you would have a picture that looks something like this. So then you would say, all right, if it's in equilibrium, I need to say the sum of my forces is 0, which means I would write an equation, this plus this minus this equals 0, because it's in equilibrium. But then you would also have to do sum of the torque equation has to be 0. And this is where you have to decide where the axis of rotation is. In some problems, it's pretty obvious where the axis of rotation is. Okay, like, if you have a teeter-totter, and, well, guess what? The axis of rotation is going to be there, like, duh. But some problems like this, you get to decide. And it doesn't matter where you decide. You can decide any place. But my solution or my suggestion would be pick some place that's going to make the problem easier. What do I mean? Well, pick some place where I'm not going to have to worry about one of those forces. So, for example, let's say you had, I picked the axis of rotation right there. Why would I do that? Because if I pick the axis of rotation right there, that's going to make this have no torque, no lever. And then you would do this, okay? And I recommend you guys kind of think about it like this. All right, this force is going to cause it to rotate that way. That would be counterclockwise. Both of these forces are going to cause it to rotate that way. So if I was writing my torque equation, okay, it would be force times lever arm for this guy, minus force times lever arm, minus force times lever arm. But here's where you guys got to be careful. Let's say I picked a different axis of rotation. Let's say I picked, right here, okay? I picked that as my axis of rotation. I can still work it out and I can still do the problem correctly, but if you guys take a look, okay, this causes it to rotate that way. This also causes it to rotate that way. So if you were setting up your torque equation, it would be this times that lever arm plus this times that lever arm minus this times that big lever arm. Okay? So again, it's not about the direction of the force, it's about the direction of the torque. So hope that helps. Bye, kids.